Okay, so we are live. So everyone, welcome to COMP2521, 25T1. So this is data structures and algorithms. So what we're going to talk about in the first hour is a little bit about what the course is going to be about and the assessment and other admin related stuff. All right, so first of all, my name is Kevin. I'm going to be your lecturer for this course. We're going to talk about introduction. Okay, so what is this course about? Well, the course is about data structures and algorithms, right? And we can relate it to the first course that you did in Comp Sci or degree, which is COMP2511. Right? I like to think of it as COMP1511 is covering the basics of programming, the fundamentals of programming, right? So you would have learned about how to write simple programs, right? How to use if statements, while loops, and simple things like arrays and linked lists, right? But COMP2521, the goal is to get you thinking not as just a programmer, but as a computer scientist. Right? And what does that mean? What does it mean to get you thinking like a computer scientist? Well, first of all, what should a computer scientist know? A computer scientist should know fundamental data structures and algorithms, right? And they should also be able to reason about efficiency, right? About how effective a particular choice of data structure or algorithm is, right? Given a problem, you want to choose the best solution for that problem, right? So that means we also want to be able to analyze how well, how efficient our program is going to run, how much space or memory the algorithm takes, and so on. Okay? So yeah, for those of you in the chat, in future lectures, I'll have a webcam. I'll put a webcam in the bottom corner, so you'll be able to see me, but not this lecture. Okay, but let's talk a little bit about data structures and algorithms first. So does anyone want to hazard a guess as to what a data structure is? Yes. Yes. Yes, it's a way to structure data, exactly. So, right, it's a way to store data in memory, right? And you already would have covered some basic data structures in COMP1511, like arrays and linked lists, right? These are both ways of storing, organizing data, right? And does anyone want to guess what an algorithm is? Yeah.
A procedure to do something.
Yeah, exactly. It's a procedure to do something. Right? So it's a set of instructions to achieve some specific purpose, right? So you guys would have already written a whole bunch of algorithms in 1511, right? But in 2521, we're going to look at algorithms at a slightly higher level of abstraction. What I mean by that is that we're going to focus on the high-level details and not worry too much about exactly how things are done at the low level. Right. And that's because when we're solving complex problems, right, and we have a complex algorithm or a set of instructions, we don't want to get worried about the low-level details, right? Like how to insert something into an array, or how to search for something in an array, right? So yeah, we're going to look at data structures and algorithms from a slightly higher level of abstraction. Okay, so what do we assume that you know coming into this course? Well, hopefully most of you have done 1511. Hands up if you've done 1511. Yes, most of you would have. Some of you might be coming from other universities or from abroad, so you might not have used C. But here in this course, we assume that you can use C because we're going to be using C throughout this course. Right, so we hope that you can use C to solve simple problems like those from your intro course. And we expect that you know how to use fundamental control structures, right, like if statements and while loops. Okay, and we also expect you to have had experience working with arrays and linked lists, right? And of course, pointers and structs. Okay, and what are we going to cover in this course? Well, data structures, right? So we have data structures like trees, graphs, hash tables, and tries. So these are all very useful data structures. And we'll see how to implement them, how they work, and so on. And also analyze them. And we'll also be analyzing our data structures and algorithms in terms of both time, so how efficient are our algorithms and data structures, and how much memory they take. There's a question in the chat asking, will we do segment trees? So unfortunately, no segment trees in this course. But the follow-on courses might cover segment trees. Okay, and we'll also be covering sorting and searching techniques. So these are very simple problems, right, that you probably would have done, as a child even, right? Sorting things, searching for things. But we're going to be looking at how we can sort and search for data at scale, right? What happens if we have 1 million items, right? How do we sort through these items or search through these items efficiently? All right, and we'll also be covering a very interesting data structure called graphs, right? And related to that, algorithms on those graphs. Okay, so who here has used Google Maps in the last month, right? Or the last year, right? So if you've used Google Maps, you would have used indirectly a graph algorithm, right? Because how does Google Maps find the shortest route or the fastest route from A to B, right? It would have used some algorithm, right? And not only that, but we want these algorithms to be efficient, right? Because who wants Google Maps to take 30 seconds to find a route, right? If it did take 30 seconds to find a route every time, people wouldn't use it, right? What we want to do is come up with algorithms that are efficient so that they can improve quality of life, right, for regular people. Okay, so by the end of this course, what do we expect you to be able to do? So we hope that you'll be able to implement solutions to a wider range of problems, right? Because we're covering a whole bunch of new data structures and algorithms. And we want you to be able to analyze the characteristics, the performance characteristics of algorithms and data structures. Right? And hopefully, given a problem, you'll be able to make a decision, a good decision as to which data structure or algorithm to use. Okay, so here are all the people involved in the course. There's the course convener, who is John Shefford. There's me. Our admins are Ethan Brown and Ryan Burley. You might have heard of some of them. And then we have a team of 43-ish tutors, and they're all looking forward to helping you learn and grow your knowledge in this course. All right, so the course website is WebCMS, so hopefully you've all been on the website and you've looked around and seen the lectures page and timetable and so on. And our email address is cs2521@csc.unsw.edu.au. Please don't email me directly for things. Send it to this email address, because this way all the other admins will be able to see the email and we'll be able to get back to you quicker. Okay. Cool. So, and also, email is for admin-related questions only, right? So if you have a question about course content, please post it on the forum instead. Because that way, more students will be able to see it, and the answer will be more helpful to more people. Okay, what are the different components of the course? Well, we've got lectures, which we're doing right now. We also have tutorials, labs, and in terms of assessments, we have the lab exercises, quizzes, and assignments, and of course the final exam. Okay, we have 4 hours of lectures a week. You guys probably know what time they are by now. So the Tuesday lecture is in this lecture theatre, Matthews A, and the Thursday lecture is in Keith Burrows Theatre, all right? And we're live streaming to YouTube, and you can feel free to ask questions in the chats. Yeah, if you're in the lecture theatre, you can also ask in the chat because we've got some lovely tutors who are answering questions on there. Yeah, so you'll be able to get an answer. Okay, and the recordings are going to be on YouTube. They should be uploaded automatically after the lecture is over. Okay? Cool. So the point of the lectures is to introduce the topics, right, and cover the theory. But the tutorials and labs are really where you solidify your knowledge and understanding, right? So every week you have a 1-hour tutorial followed by a 2-hour lab. Right, so the tutorials and labs start this week, and their job is to clarify lecture material, right, and also to ask you higher level questions, right, to get you thinking more. All right, so yeah, please go to your tutorials. I know a lot of you might not do this, but try to read and attempt the problems by yourself beforehand. Right? Because that way you'll get a sense of what you're confused with and what questions you can ask, right, your tutor. All right? And in tutorials, make sure to ask if you don't understand something. Right? And your tutor might have sent you an email, or they will send you an email before your tutorial. If you're confused about something, you can also email your tutor, right? Or you can also ask on the forum. Okay, so for labs, well, the labs are after the tutorials. So yeah, in labs, you'll be working on some lab exercises, right, which are mostly small scale problems, right, and analysis tasks. Right, so yeah, so with lab exercises, you should do them individually, right? Please don't copy from someone else or use AI. There's more on that in a bit, but yeah, please try to do them by yourself. And if you have trouble, there will be help sessions, right? Starting from week 2. So yeah, there will be plenty of help available. Yeah. And the lab exercises need to be submitted, right, via Give, right? In 1511, you would have used Give to submit your labs and stuff. Also submit your lab exercises here using Give. The deadline is Monday, 5 p.m. of the following week, right? So this week's lab, that means, is due Monday, 5 p.m. next week. Okay, so that's that. So you need to submit your work, but in this course, most labs also have a hand marking component, right? Some of them don't, but most of them do. So what that means is that you'll need to show the work that you've done, that you've submitted to your tutor, right, within 2 weeks of the lab, right? So that means this week's lab has a hand marking component. So after you've submitted, remember you need to submit by 5 p.m. Monday next week. You'll have week 2 and week 3 to show your tutor your work, okay? And in terms of your final mark, your labs make up 15% of that. Okay, we also have quizzes. So we have weekly quizzes on WebCMS, and what they do is they will test you on your knowledge of the previous week's lectures, right? And knowledge, but also understanding, all right? So yeah, so these should also be done individually, and they're also due Monday, 5 p.m. the following week. Okay, so the quizzes aren't timed. So when you open the quiz, it's not going to be like you have 1 hour left, right? The quizzes will remain open, and you can submit them whenever you want. You can submit multiple times, but only your last submission will be marked, right? So yeah, what you can do is you can start on Sunday, submit the quiz, right? And then you can come back and then do the remaining questions. All right, and quizzes are worth 10% of your final mark. Okay, we also have assignments. So, right, 2 assignments, and each of them are worth 15% of your mark. Okay. Cool. So late penalties. So they're going to be the same for labs, quizzes, and assignments, right? So this will be 0.2% of the maximum mark taken from your raw mark, right? So that can sound a little confusing. So just because it says maximum mark doesn't mean it's deducted from the ceiling, right? What this means is that we take 0.2% of the maximum mark. So if you're 5 hours late, for example, then we'll calculate what 0.2% of the maximum mark is times 5, and then we would deduct that from your raw mark, right? So, yes. And then, yeah, so in terms of late submissions, you can't submit later than 5 days, okay? Cool, and solutions. So we try to release solutions as soon as we can, right? But what that means is that for labs, we'll release them 12 days after the due date, right? So the reason why it is so late is because we have to take into account people with special consideration and extra provisions, right? So, yeah. In terms of marks, we'll release them a week after the due date. And for quizzes, the answers will be released 5 days after the due date. Okay, and for assignments, sample solutions aren't released. Okay, and also for assignments, there are 2 parts to the marking, right? There's the order marking and the hand marking. So the order marking will be released earlier than the hand marking, right? Because it will take longer for your tutor to do all the style marking. Okay, and we also have a final exam. So the final exam is like 1511, or should be like 1511, 3 hours. It's going to be in the CSE labs, and there will be limited resources provided, right? So there'll definitely be documentation, of, C, manual pages, and so on. But yeah, in terms of other resources, we will be deciding that shortly. Okay, and the final exam what it will have 2 sections. It will have a theory section with short answer questions and programming questions. Right. And the exam hurdle is 3 parts. So you have to score 40% on the final exam overall. And you also need to have shown that you have some basic competency in both sections, right? So 25% in the theory section and 25% in the programming section, right? What I mean by 25% is 25% of the marks of the theory section, right? So if the theory section is 40 marks, then you need to get at least 10, right? if the programming section is 60 marks, then you need to get at least 15. Right. Okay, so a little bit about special consideration. So if you've been impacted by circumstances outside of your control, and yeah, it severely impacts your ability to complete any assessment, then you can apply for special consideration, right? And you can look at how to apply here. Okay, let me check the chat. So the question is, will you be provided algorithms during the exam? So in previous terms we have, I think that will likely be the case. So we'll still provide a reference page with the algorithms and data structures. So that's likely. Yeah. Okay, so this is the summary of the assessment, right? 15% labs, 10% quizzes, 15% for both assignments and 45% for the exam. Okay, and to pass the course, you have to get at least 50 overall and pass the exam hurdle. Okay, so now a little bit about academic integrity, right? So plagiarism, cheating, all of the assessments that you complete should be your own work, right? So that's labs, quizzes, and assignments, right? So yeah, the reason is, right, we want you to gain the skills and knowledge yourself, right? In order to be able to use that knowledge in future courses, right? All of the future courses in your degree are going to build upon data structures and algorithms, right? No matter what area of computer science you go into, some concepts from this course are going to be relevant in future courses. Right? So we want you to be able to have the knowledge for yourself. Okay, and yeah, plagiarism. So please don't plagiarize. We will check for plagiarism, and you may be penalized if you are caught plagiarizing, right? And other negative consequences. Okay, and of course there is the discussion of AI, right? AI tools. So what can you use them for? Can you use them at all? So first of all, using AI tools to solve the problems given to you in labs, quizzes, and assignments is not allowed, right? So don't use them to generate answers or solutions. However, you can use generative AI for learning, right? If you think AI gives you good summaries of topics, which it can do sometimes, then you can use that for that purpose, right? But you still need to be critical of any output that you get from AI, right? Because AI, like the output that you get from like ChatGPT and so on, can be pretty convincing, right? So you might end up believing what it tells you, but it might not give you the most correct information, right? So yeah, if you have any questions about content in this course, it's best to ask on the forum, right? Because then you get more accurate information. Okay, and yeah, the last point, AI tools, so they can really help you be more productive, right? If you're a good programmer already, right? And that's because the output that it gives you, you can tell whether the output is good and useful or irrelevant and not very useful, right? Using AI tools, you need to have already a good understanding of the language or system or thing that you're working on. Okay, in terms of resources, so first of all, we have the Discourse forum, right? So Discourse is a kind of new forum system that we are testing out, that a bunch of CSE courses are testing out. So yeah, please, if you have any questions, go in there and post a topic. Right. And since it is new, we'd appreciate some feedback on the forum. Right. So if you have any feedback on the forum, there is a form that I'll share that you can put feedback in. Right. Of course, there's also the tutors and labs for resources, right, where you can ask questions to your tutors. There'll also be weekly consultations where I'll be available to help answer any questions about lecture content and course content in general, and they'll start next week. Right? And they'll be after the Thursday lecture. Right? That will be 11 to 12. Right? And we'll also have help sessions starting from next week. Right? So we're still organizing them, but the schedule will be on the course website. Okay, so now a little bit about expectations. So what we expect from you, what you can expect from us. Right, throughout this course, please make sure to check your email regularly. Right, and why is that? Because announcements will be sent to your email. Right, you know, what if you get an extension for something and you don't know about it? Right. Right, the announcements will be sent to your email, so if you don't check your email, then you might not see it. So make sure you check your email. Your tutor will also send you emails, right? Some of your tutors are really hardworking and they've written notes, right? And they are going to share them with you. So yeah, make sure to check your email. And reminders of unsubmitted work are also going to be sent to your email. So yes, please check your email. Okay, another thing is that we want you to read the spec before asking questions, right? So that's for the labs, for the assignments, right? We're happy to answer questions about, content, course content, right? But it does annoy us a little bit when you ask a question that's already answered in the spec, right? So yeah, please make sure to read the spec. Okay, and one more thing is debugging, right? So please try to debug your program yourself before asking for help, right? Because debugging is a really valuable skill, right? You'll need debugging skills when you go out there and you work in industry, right? And you'll also need them in your final exam, right? Because you won't get any help in the final exam. Okay, so how can you debug? So you can add print statements to your program, right? That's what you might have done in COMP2521. You might use GDB. So GDB is a debugging tool, and we have an extra lab for that we'll release this week. All right, and you can also draw diagrams, right? Drawing diagrams can be really helpful when you're debugging things like linked lists, right? Because you can use them to visualize what the program is doing, right? When you change a pointer, right, in your diagram, you can change where the arrow is pointing to, right? That's very helpful. Okay, and on the flip side, what can you expect from us? So you can expect regular announcements, right? So we'll make weekly announcements on the course website. We'll release lecture slides before lectures, so that's going well so far. And we try to not have too many typos and mistakes in lecture slides, but if you do find a major typo, then please post on the forum and we'll fix it. Okay, and you can also expect things to be released on time, so shoot questions and lab exercises, assignments, and marking. Okay, so here's some advice, right, to get through the course. So please keep up with lectures, right? So why? Well, because the labs and quizzes will require you to know the content from the lectures, right? So please try to keep up with lectures. The recordings will be available immediately after, so that's not going to be a problem. And there are lots of other lecturers who have taught the course in the past, right? So what I'm saying is, if their teaching style does suit you better, then you are free to watch those lectures. But just be aware of the changes in the course, right? In the course content. So yeah, just be aware of that. Make sure to attend tutorials, and especially if you're falling behind, right? And your tutors aren't going to judge you for falling behind. Most of them have probably been there before. And yeah, they'll happily help you, right, with anything you need. All right, another important thing is try to understand the course content, right? Not just memorize it, right? Why is that? Because first of all, understanding something, I think, makes it easier to remember, right? So you're just cramming things in the final exam, for the final exam, you're not gonna absorb anything, right? It's not gonna be retained. So yeah, just make sure to try to understand. Feel free to ask questions if you're struggling to understand something. And another thing is make sure to practice programming, right? Don't just do programming in the labs and in the assignments. Make sure to do additional programming outside of classes, right? You should be doing programming a few times a week at least on your own, right? And what can you do during those sessions? I mean, one thing you could do is, we will cover a lot of algorithms and coding in the lectures. And so what you could do is, after the lectures on some other day, you could revisit the lecture content and try to write the code up for yourself, right? See if you can do it. See if you understand the content well enough to reproduce what we covered in lectures. Right, another thing you could do is, we have a whole bunch of practice exercises on the course website, right? So you can try out those practice exercises, right? So there are exercises for the different data structures, right? You can try the practice exercises for the topics that we've covered, right? Because programming is a skill, right? The more you practice it, the better you get. Okay, so in the chat, there's a question about, will there be scaling for the final exam? It depends on the mark distribution, right? So yeah, that's the answer, it depends. And another question is it possible if there are recommended LeetCode questions that you guys put up for us to have a go? So there is a list of LeetCode questions floating around somewhere that we can share later. But the answer to that is yes. So yes, there is. Okay, and finally, make sure to engage with the course as much as possible, right? Ask questions if you don't understand something. Go to consultations, go to your tutorials, right, and do practice exercises. Okay, so yeah, if you put in the effort, you can improve, right? So this is a course where you really get out what you put in. Okay, and finally, course feedback. So we have a form where you can submit any feedback you want anonymously. You can also share your name if you want, but yeah, it's anonymous. Yeah, so if you want to share any feedback about anything in the course, that's lectures, tutorials, labs, assignments, the forum, yeah, go to this form and submit something. Yeah, give us some feedback. Okay, and finally, so the content in this course is drawn from a lot of previous lectures. So Jushank, Angela, John Shefford, and so on. Okay, so that's the intro to the course and the admin stuff. So what we'll talk about now is a little bit about the tooling we use in the course, right? And what you'll be using in labs and assignments. Okay, so first of all, compilers, right? So in 1511, you would have used DCC, right? And the way you would have compiled your code is you would have done DCC -o program.c, right? So DCC is kind of like a compiler for new programmers, right? So it gives you friendly error messages, right? And it tries to explain things in a way that's easy to understand for new programmers, right? But now that you are no longer a new programmer, we are using a different compiler called CLang or Clang, which sounds cooler. And fun fact, DCC actually uses CLang under the hood, right? So what it does is it compiles your program using CLang, and then it wraps it in some other software that creates more friendly error messages. Okay, so this is how we're going to compile things in this course. Right, so what are the different parts of that compilation command that I just showed you? Well, first of all, we have Clang, right? Then we have -w all. So this isn't wall, this is w all. And what this means is it enables all warnings, right? Or almost all warnings, right? And what this will do is it'll catch many possible mistakes that you've made. Okay, then we've got w-error. So what w-error does is if you don't, okay, let me explain what happens if you don't put w-error. So if you don't put w-error and your program compiles with warnings, it will still compile, right? And you'll be able to run the program. What w-error does is it changes the warnings into errors so that your program no longer compiles if it has any warnings. And this is good because warnings generally mean that you've made a mistake, right, in your program. So you don't want to run the program if you know that you've made a mistake. Right? Okay, we've also got -g. So what -g does is it preserves information for debugging, right? And it also allows the program to produce nicer error messages, right? When the program spits out an error message, it'll tell you what function the program was in when the error happened, what line number it was in, and so on. Okay, cool. What we'll also use when compiling in this course is sanitizers. Right, so what sanitizers are is that they are plugins that instrument your code. Right, what that means is when your program compiles, the sanitizers will insert extra code into your program to check for errors. Right? So the main sanitizers that we'll be using are address sanitizer, leak sanitizer, memory sanitizer, and undefined behavior sanitizer. Okay, and we'll talk a little bit about what each of them do. So first of all, address sanitizer detects invalid memory access. Right, so this is things like out of bounds array access. So if you declare an array of size 10 and you try to access index 10, right, that's not valid. So address sanitizer will catch that. We also have use after free errors. So you guys know what a use after free error is, right? It's when you free some bit of memory and then you access that bit of memory later on. Right, so that's not valid, and the sanitizer will catch that. And double free errors, that's when you try to free something twice, and so on. Okay, so to use address sanitizer, we compile with this flag, right? -f sanitize equals address. Right, and our make files, which we'll get to in a bit, compile with address sanitizer by default. Right, so all the stuff that we're covering now will also be covered in your first lab exercise. Right, so it'll go through the sanitizers and the different errors that you might get, so that you will, when you work on future lab exercises, you will know how to interpret the error messages given by your program. Okay, so here is an example of a program with a bug that will get caught by a dress sanitizer. All right, so have a read of this program and see if you can spot the problem, and I'll give you a bit of time for that. Okay, so can anyone see what the problem is? Yes? Yes, exactly. So we're initializing an array of size 5, and then we read into the array, but we don't stop when we've read 5 numbers, right? 5 elements. We just keep going, which means the program is going to try to write outside of the array, right? Past the 5th element. Right, so that will cause an error, and the error message that you get is going to look like this, right? So, don't be scared by this. Once you get more practice with looking at error messages, which you will get in this week's lab, so there's a part which is all about interpreting these error messages, you'll be able to immediately figure out where to look and figure out where the error is happening. Okay, secondly, we have leak sanitizer. So what leak sanitizer does is, it detects memory leaks, right? And to use leak sanitizer, we compile with this flag. Okay, so here's a very simple program with an error, with a memory leak, and it would get caught by leak sanitizer. Right, so we've malloced some memory, but we haven't freed it. Right, another sanitizer that we'll be using is memory sanitizer. So what that does is it detects use of uninitialized memory. Right, so if you're using uninitialized memory in a condition, right, then that's a bad thing, right? Because the value might be anything, right? If you don't initialize a variable, it might contain any value. That means if you run the program multiple times, sometimes the condition might be true, sometimes it might be false. So you get some non-determinism. Your program does different things, even though you're running it the same way each time. Right, so that's bad. So memory sanitizer will catch these kinds of errors. Right, and finally, we have undefined behavior sanitizer. So this will detect a bunch of undefined behaviors, right, like overflowing an integer. Okay, and that's how we compile with undefined behavior sanitizer. Okay, so that's the sanitizers. So again, you'll get a lot of practice using these sanitizers and reading the error messages from them in this week's lab. Okay, and next up, another tool that might be useful is Valgrind. Right, so Valgrind is a very powerful tool that you can use to find memory leaks and detect memory errors. Right, so these kinds of errors kind of overlap with the ones that sanitizers catch, but Valgrind, it works in a slightly different way, right? So you don't compile your program with Valgrind. When you use Valgrind, you run your program under Valgrind, right? So you don't compile with Valgrind, but you can run your program with it, right? And while your program is running, it'll tell you what memory errors your program has made, and at the end, it'll tell you what memory has leaked. Right. Okay, and the thing with Valgrind is that it's not compatible with sanitizers. So if you want to use Valgrind, you need to compile your program without sanitizers. Okay, and finally, the last bit of tooling that we will use is make. Right, so in one of the previous slides, you would have seen that the compilation commands we use are pretty long, right, and annoying to type. Right? We don't want to have to type this compilation command every time we want to test our program. So what we use in this course is make, right? And what make does is it lets us specify the dependencies of our program, right? So for every program that we write, in our make file, we'll specify what are the C files that the program uses, and what are the compilation flags that we're going to use to compile this program, right? And if we do have a make file, all we have to do to compile our program is to type make, right? And you'll be able to try that out in the lab this week. Okay, cool. So that is the intro to the course. And after every lecture, there will be this slide that has a link to the feedback form. So if you do have any feedback, please feel free to drop some on the form and we'll have a look at it. All right, but yeah, that's it for the first half, the first hour. So we'll take a quick break now of, well, I guess it's 11:55, so we can have a 10-minute break and we'll come back at 12:05, where we cover our first topic, which is recursion. All right, so see you then. Thank you. So, all right, now let's get back into our first topic, which is going to be recursion. Right, so recursion is a really important programming concept that you'll be using throughout this course. So it's really important to understand what it is. Okay, and hopefully after this lecture, you'll make sense of this picture. So this is an example of recursion. And hopefully this already gives you an idea of what recursion is. Okay, so what is recursion? Right, so you might have heard of recursion as a function calling itself, right? But what I like to think of recursion as is it's a problem-solving strategy, right? Where we solve problems by solving smaller versions of the same problem, right? So this is why we use recursion. So there are often problems that we can solve by solving smaller versions of the same problem, right? And when we solve problems recursively in programming, we end up having functions that call themselves, right? We end up having recursive functions. Okay, so recursion doesn't just exist in programming, right? It also exists, outside, and an example of that is this thing called the Sierpinski triangle, right? So what you see here is that it's a kind of structure that contains self-similar structures within it, right? If you zoom in to this, to one of the triangles, one of the three main triangles, you'll see an identical structure, right? An identical picture. Right, so if you were to draw this triangle, you could do it recursively, right? What you could do is you start with a triangle, right? And then what you would do is you would zoom into the top part of the triangle, zoom into the bottom left and the bottom right, and you would draw, an upside down triangle in the middle, right? You would just repeat that until you get something looking like this. Right, another example of recursion is building a pyramid, right? So I don't know if you've heard of this game, you might have heard of it, but here's an example of a pyramid, and we can describe how to build the pyramid in different ways, right? One of them is we can build it layer by layer, right? So if we want to build a 7 by 7 pyramid, then we would first put a 7 by 7 square of blocks, then we'll put a 5 by 5 layer of blocks on top, then 3 by 3 layer, then finally a single block on top. Right, and that's how we build a pyramid iteratively. Right, you can imagine how we might implement this using a while loop, right? And that while loop might look something like this. So this is not code, but this is like an English description of the loop. So what we would do if we want to build a pyramid of width n is we would start with the width being equal to n, right? And then we would build a layer of blocks, which is w by w, right? And then we would decrement w by 2 each time until it's 1, right? And until we've placed that one block on top. Okay, so that's how we build a pyramid iteratively. We can also think of building a pyramid recursively, right? So what you'll notice in this image is that this pyramid contains smaller pyramids within it, right? This pyramid also contains a 5-width pyramid, right, on top of a 7 by 7 layer. It also contains a pyramid of width 3, right? So what we can essentially do is describe how to build a pyramid in terms of building smaller pyramids, right? So that's what this image is depicting, right? To build a 7 by 7 pyramid, or 7-width pyramid, we can first build a 7 by 7 layer of blocks, right? And then we can build a pyramid of width 5 on top, right? So that's how we describe building a pyramid recursively. And if we were to implement this or write the procedure for this, it might look something like this, right? To build a pyramid of width n, we'll build an n by n layer of blocks, right? Then we will build a pyramid of width n minus 2 on top, right? Makes sense, right? To build a 7-width pyramid, we put a 7 by 7 layer, then we built a pyramid of width 5 on top, right? So if you were to follow these instructions, you would probably, end up with a pyramid, right? But imagine a computer try to interpret these instructions, right, and build a pyramid. What's a problem with this that would arise? As a human, you would understand these instructions perfectly, right? But what trouble might the computer have with understanding these instructions? Yes? Yeah, so it won't know when to stop, right? Imagine when n is equal to 1, right? Then what is it going to do? It's going to build a 1 by 1 layer of blocks, right? Then it's going to try to make sense of the second instruction, which is to build a pyramid of width 1 minus 2, right? Which is negative 1. How does it build a pyramid of width negative 1? That doesn't make any sense, right? So, yeah. The problem is that we don't have a condition for stopping the recursion, right? So what we need is something called a base case, right, or a stopping condition. So what we got to do is first check if n is 0 or negative, right? If n is less than or equal to 0, then we do nothing. Otherwise, we do what we did before. So we build an n by n layer, then we build a pyramid of width n minus 2 on top. Okay, so that's an example that doesn't involve any programming, right? But here we have an example of a mathematical example of recursion, right, which is factorial. Okay, so you probably all know what factorial is, right? Factorial of n is the product of all the numbers from 1 up to n. Right? So n factorial is n times n minus 1 times n minus 2 times blah, 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 all the way down to 1. Okay? So, of course, we can all implement this iteratively using a loop. Right? So this is how you would do it. Right? So I think all of you would be able to do this. Right? So we have a result variable that we initialize to 1. Then for all the numbers from 1 to n, we multiply it by I, right? By that number. Okay, so that's the iterative method. But we can also implement factorial recursively, right? And in order to implement it recursively, we need to make an observation about how we can express factorial in terms of a smaller factorial, right? And if you write out the definition of factorial, then you might notice something, right? So n factorial is n times n minus 1 times n minus 2 times all the way down to 1. But this part of the formula is just n minus 1 factorial, right? So what that means is that we can express n factorial in terms of n minus 1 factorial, right? So an example of that is 4 factorial. So 4 factorial is 4 times 3 times 2 times 1, and that's equal to 4 times 3 factorial. Right, so if we were to implement this, we would get, if we try to implement this, we might get something like this, right? So in our factorial function, we return n times factorial n minus 1. Right, but what's wrong with this function? Anyone want to? Yeah, so the problem is that if n is equal to 0, right, then it's going to try to find factorial of negative 1. Then that's going to try to find the factorial of n minus 2, of negative 2, and so on, right? So the function is never going to stop recursing, right? And if you try to run this, then you'll get an error called stack overflow, right? That's when the program is using too much stack memory, right? And why is that? I'll talk about in just a bit. But the way to fix this is to add a base case or stopping condition for n equals 0, right? So if n equals 0, we know that 0 factorial is equal to 1, so we return 1, right? Otherwise, we return n times factorial of n minus 1. Okay, and the assumption we're making here is that the input is non-negative, right? So there's negative factorial of a negative number doesn't make any sense. So we're assuming here that the user always passes in a 0 or a positive number. Okay, so here is kind of a bit of so here is an example of how factorial would be evaluated, right? How the function would evaluate factorial of 3, right? So if we call factorial and we pass it the number 3, what is it going to do? Well, 3 is not equal to 0, right? So what it's going to do is try to return 3 times factorial 2, right? So that's what it does here, right? Now, what the program is going to do is it's going to jump into factorial 2, right? Because it needs to find out what that is before it can multiply it with 3, right? So what does factorial 2 do? Well, factorial 2, it's got to return 2 times factorial 1, right? But that means the program's got to now jump into factorial 1 to figure out what that is, right? So what does this function call do? It does 1 times factorial 0, right? Finally, factorial 0 is a base case, so the function is going to return 1, right? Then we can finally evaluate all these multiplications. So 1 times 1 equals to 1, 2 times 1 equals to 2, so that means 2 factorial is 2. And then finally, we can do 3 times 2, which is 6, right? So 3 factorial is 6. Okay, so that's another example of recursion. Right, so cool. Okay, so now how does recursion work, right? So recursion involves a function calling itself, so why doesn't the program get confused? So recursion works because there's a difference between a function and a function call, right? A function is just a series of instructions for the program, right? A function call is every time the function gets called, right, what will happen is that a new stack frame will be created for that function call, right? So if you've taken 1521, hands up if you've taken 1521. So you'll have experience creating stack frames, right, using MIPS, right? But every time a function is called in a program, for example, the main function calls factorial, right, there will be a new stack frame created for that function call, okay? And that stack frame contains all the local variables used by that function call, okay? So here is what would happen if we try to run this program. So there isn't any recursion happening in this program, but just to show you what happens when a function is called. So here we have the main function calling A then calls B, and B then calls print, right? So how the stack would change when we run this program is when when the program starts, it calls main, so it creates a stack frame for main. Then when main calls a stack frame for A is created on top of main. When A calls B, a stack frame for B will be created on top of A. And then, okay, here B calls Prince, so it would actually create a stack frame for Prince, but I haven't included that here. And when a function returns, the stack frame disappears, right? So when B returns, this stack frame gets popped off. When A returns, this stack frame gets popped off, and now we only have main. Okay? Now, the same thing happens with a recursive function, right? So when we call factorial 2, for example, right, we have a stack frame for factorial 2. When factorial 2 calls factorial 1, that creates a stack frame for factorial 1 on top, right? And when factorial 1 calls factorial 0, that creates another stack frame for factorial 0 on top, right? And each of these stack frames, the important thing is each of these stack frames hold their own version of n, right? Right, because n is a local variable used by the factorial function. Right, so in this stack frame, n is going to be 2. In this stack frame, n is going to be 1. In this stack frame, n is going to be 0. Okay. Cool. And a little bit of terminology for recursion. So when the function recurses, that's called winding. All right. So the function is winding up. And when the recursive calls return, or when the stack is shrinking, that's called unwinding, right? And we'll be using unwinding more than winding, but yeah. Okay, and what you can experiment with is try putting operations like print statements before a recursive call and after a recursive call, right? And what you'll see is that any print statements that you put before the recursive call happen during winding, right? So on the way up here while the stack is growing, right? And any operations that you put after the recursive call happens during unwinding, right? So they happen in kind of reverse, right? In the reverse order of when the functions are called, right? And I can show you an example of that here. So here I have a factorial program, right? And I have some print statements, right? So the first print statement I'm putting before the recursive call, right? And the next print statement I'm putting after the recursive call. And we'll see that the print statement that happens after the recursive call happens in kind of reverse, right? In the reverse order of the function calls themselves. So let's try to run this program. And we've got to enter a number, so I'll just enter 4 here. So we can see that the print statements I put before the recursive call, right, happen in order of the function calls, right? We've got factorial 4 entered, factorial 3 entered, factorial 2 entered, and so on. And the print statements that I put after the recursive call happen in reverse order, right? So factorial 0 returning, factorial 1 returning, factorial 2 returning, and so on. Okay. Cool. So that's how recursion works, right? And we'll go through a bunch more examples. Okay, but first, let's talk about recursion on linked lists, right? So we can solve a lot of problems on linked lists recursively, right? And remember what recursion is. Recursion is where we solve problems by solving smaller versions of the same problem, right? So how does this apply to linked lists? Well, if you look at this linked list, right, you will notice that a linked list contains smaller linked lists inside of it, right? So this linked list that contains 4, 5, and 7 also contains a small linked list that contains 5 and 7, and that list contains another small list that contains just 7, and even that list contains a small list that's empty, right? So what that means is that when we're trying to implement a linked list function, right, what we could do is we could pass the rest of the list into the function itself, right, recursively, and sometimes we might be able to use that to solve linked list problems, like this one, right, like summing a list. Okay, so how do we sum a list recursively? Right, first of all, we have a base case, right, for an empty list, right? So the base case, remember, is the case where the recursion stops, right? And you don't need any recursion anymore. So it's where the problem is so simple that you don't need any recursion. And the base case for a linked list is usually an empty list, right? For some problems, you might have multiple base cases, but here we just have the case of an empty list. And the sum of an empty list is 0, right? So that's what we would return if the list was empty. Okay, but what if our list is non-empty? Right, so the thought process is, well, if I find the sum of the rest of the list, right, and that is a smaller version of the same problem, right, which is to sum a list. If I found the sum of the rest of the list, then all I need to do is to add the value in the first node to that sum, and that would give me the sum of the entire list. Right, so here's a kind of breakdown of how the recursive function would work, right? So to sum this list, 3, 1, 4, well, first of all, let's sum the rest of the list, right, 1, 4, and then we'll add that to the first value, which is 3. Right? How do we sum that list containing 1 and 4? Well, we can find the sum of the rest of the list, which is just 4, and then add 1 to it. Right? How do we find the sum of this list? Well, we can find the sum of the rest of the list, which is empty now, and we know that the sum of an empty list is 0, right? That's our base case. So we can return 0, and then we can now do all of our additions, right? So 4 plus 0 is 4, 1 plus 4 is 5, and 3 plus 5 is 8. Okay, and here is the code for summing the list recursively. Right, so here's our base case. Right, we return 0 if the list is empty, and otherwise we find the sum of the rest of the list, and we add on the first value. Okay, so when we're solving problems recursively, I don't want you to think of it as we have a version of the solution that uses a loop, and we want to convert it into a recursive function, right? Don't think of it like that. Remember what recursion is. Recursion is where we solve problems via solving smaller versions of the same problem, right? So try to think about how can I solve this problem in terms of a smaller version of the same problem. Right, so here's my kind of advice for writing a recursive function. Right, first you have to think. Right, that's the hard part. Right, how can you express the solution in terms of subproblems? Right, and then next up, what would those subproblems even be? Right, for a linked list, usually it's going to be the rest of the list. Right, what's the sum of the rest of the list? And then next, how do you relate the original problem to the subproblems, right? How do you solve the original problem in terms of the subproblem? Well, for the summing the list problem, if we found the sum of the rest of the list, and we added the first value, then that gives the sum of the entire list. Right, and then next up is what are the base cases, right? So what are the cases where the problem is so simple that you don't need any recursion, right? That the problem just can't be broken down any further. Okay, then after we've thought about all of these things, we can now implement our solution, right? So when you implement a recursive function, you usually implement the base cases first, right? Because there's no recursion involved, and it's really simple. And then you implement your recursive cases, right? And my advice for implementing the recursive cases is each subproblem typically corresponds to a recursive call, right? So in the case of summing a list, summing the rest of the list means we call the function recursively on list next, right? And that's what it means. So each subproblem typically corresponds to a recursive call. And when you make the recursive call, I recommend that you assume that the function already works for the subproblem, right? So when we're writing this function and we call list sum on list next, right? You assume that the function already works on list next, so you assume that it gives you the sum of the rest of the list, right? And then, yeah, you can add on list value, right? So you got to assume that it works because you haven't finished writing the function yet, right? How do you trace through what the function does if you haven't finished writing the function? So assume that the function works already, and then go from there, right? It's kind of similar to mathematical induction, right? If you've done that in high school math or uni math, right? In mathematical induction, there's a step where you assume that the statement is true for n equals k, right? And then you prove that it's true for k plus 1, right? When you initially assumed that the statement is true for n equals k, did you know it was true? No, you didn't, right? But you just assumed that it was. And then, yeah, once you prove that the statement is true for k plus 1, you combined that with the base case to show that it's true for everything, right? Yes. Okay, so here are some exercises that we can go through. So first of all, given a linked list, let's try and print the items in reverse. Okay, so let's try and program this. List print reverse. Okay, and really think about this for a second. Okay, so let's try to think about this in terms of how can I print a list in terms of printing, how can I print a list in reverse in terms of printing a smaller part of the list in reverse, right? So does anyone have any ideas? Yes? Mm-hmm. Yeah, so that was pretty much it. But for recursive problems, I want to refrain from using the word traverse, right? Because that kind of implies that we're using a sort of loop, right? So for printing a list in reverse, so we have a case where the list is going to be empty, right? So if the list is empty, then there's nothing to print, right? So we just return. Okay, so if list equals null, return. But how about the recursive case? So what do we do first if we want to print out the list in reverse? Yeah, so we call our function recursively, and what do we pass in? Yeah, so we pass in list next, right? So, okay, so the thought process here is, in order to print out a list recursively, right, list in reverse recursively, how can I do that in terms of printing out the rest of the list recursively, right? So the thing is, if I print out the rest of the list recursively in reverse, right, and then I print out the first value, then I have printed out the entire list in reverse, right? You have to think about it logically, right? So that's how, so logically that checks out, right? If you think about it. So what we do is we print out the list in reverse, right? The rest of the list in reverse, then we print out the first value. So after we call list print reverse, we're going to call a print on list arrow value, and that's it, right? So now if I compile and run the program, okay, it's going to ask me to enter some values. So let's go with this 1, 2, 3, 4, 5. And if I press Control D, it will print out the list in reverse, right? So the list is 1, 2, 3, 4, 5, and we print out 5, 4, 3, 2, 1. Okay? So that was a first simple example of recursion. So let's try the next one. Okay, so given a linked list, we want to print every second item. Okay, so if my list is 1, 2, 3, 4, 5, 6, then I want to print out 2, 4, 6, right? So let's try and do this recursively. All right, so I got list print every second value. Okay, so let's think about this for a second. All right. Okay, does anyone have any ideas?
Like similar to the previous one, we can put list next, and then for printing list next.
Yeah, awesome. So, yeah, so printing every second value, you can imagine how we could implement printing every value, like printing the entire list, right? How we would do it is we would print the first value in the list, then we would print the rest of the list, right, recursively. Right, so that's how we would print all the items in the list recursively. But if we want to print every second value, then we want to kind of jump ahead by 2, right, every time we recurse. Right, so what we'll do is we'll first print, so not including the base case for now, what we'll do is we'll first print out the second value in our list, right, so not list value but list next value. Okay, and then we want to print out every second value in the rest of the list, right? From the third value onwards, right? So what we're going to do is we're going to call list print every second value on list next. Okay. So that's our recursive case, right? But we've got to add our base case so that our function actually stops. So what is our base case going to be? Anyone else want to contribute? Sorry, I can't see where that voice is coming from. Yeah. If list next equals to null, then we return. Okay, so let's think about what that means. So if list next equals to null, then that means we have 2 items in our list, right? So we have 2 items in our list. So we wouldn't want to return right away because we still need to print out the second value, right? So can we change this in some way? Yes. Yep, so awesome. So we can change it to if list equals to null. Then what do we want to do? Yes, so want to return. Okay, so yeah, if our list is empty, then I mean there's no second value to print, so we just return, so that makes sense. Is there something else that we are missing? Yes, awesome. So if list next is null, right? So we've got to take into account what happens if we only have 1 value in our list, right? Because if we only have 1 value in our list, then list next is going to be null, right? And then list next value is going to cause an error, right? Because list next is null. So if we have 1 item in our list, then we've also got to return, right? And since we do the same thing under both of these if statements, you could combine them with an OR, right? So if list equals null or list next equals null, return. Okay, so let's try running this program. All right, so I'm going to enter 1, 2, 3, 4, 5, 6, 7, 8, and we expect to get 2, 4, 6, 8. Right, so that's what we get. Okay. Cool. So finally, let's try exercise 3. So given a list and an index, return the value at that index. Okay, so an example is if we want to, so if the index is 0, then we want to return the first value in the list. If index is 1, then we want to return the second value in the list, and so on. Okay? So let's think about how we might do this recursively. Just get index.c. Okay, so this one is a little more interesting because it takes in an argument, right, an index. So, yeah. Anyone have any ideas about how we could implement this?
We can do a recursive column with next at index 1 is 1.
Yes, so what we can do is, well, let's try to talk through the logic of it first. So suppose I have this list, right? 3, 1, 4, 1, 5, right? And here are the indexes of the values in this list, right? So index 0, 1, 2, 3, 4, right? Now, the idea is if, let's say we wanted to get index 2 of the list, right? So I want to get index 2, so that's this value here, right? So how we could solve this in terms of solving a smaller version of the problem, right, is to say that if I want to get index 2 of this entire list, right, then that's equivalent to getting index 1 of the rest of the list, right? Or in general, if we want to get index n of the list, of this overall list, then that's equivalent to getting index n minus 1 of the rest of the list, right? So this is the thinking part, right? You've got to think about how to solve the problem in terms of the subproblem. So let's implement that recursive case now. So we got to return list get index list next index -1, right? Okay, and that's the recursive case. What is our base case? Because with this, like, the program's never going to stop. So the base case is if index is 0, right? If index is 0, then we just return whatever's in the first node. Right, so if index equals to 0, return list value. Okay. Cool. And there's an implicit assumption here that index is non-negative, right? Just like with factorial. Lists get index. So let's enter some list values, right? And let's enter an index. So let's put index 2, right? And index 2 is 4. Okay. So we did it. Okay, so those are some simple examples of recursion in a linked list. You'll get a lot of practice with recursion next week, where the lab exercise is just solving recursive problems. Okay. Yeah, so there's a question in the chat asking where we can access the fresh code. So I'll make sure to upload a starter version of the code, and as well as the finished version. Okay, so let's look at another example, which is a little more complex. And this one is appending a value to a list, right? So here we're not just returning something or printing something, we are actually modifying the list. All right, so what we want to do is add a value to the end. Okay, and what the function should also do is return a pointer to the start of the updated list. Okay, so we want to add a value to the end of the list and return a pointer to the start of the list. Right, so does anyone know why we might need to return a pointer to the start of the updated list? Any ideas? Yeah.
So you don't lose the list.
Yes, so we don't lose the list, specifically in the case where the list is originally empty, right? So if the list is empty and we append a value, then the resulting list is the node containing that value, right? And we want to make sure to return a pointer to that node so we don't lose it, okay? Cool, so here is one attempt at list append, right? So given what you know about recursion on linked lists, here's something that you might cook up. So if list equals null, if the list is empty, then return a node containing that value, right? So that's our base case. And otherwise, we just append the value to the rest of the list, right? List append list next value, and then return list. Right, so this sounds really reasonable, right? But there is a slight problem with it. Yeah, so the problem is that the new node doesn't get connected to the rest of the list, right? So here's the problem. Right, here's our code from before, and here is a list, right, that contains one value. Okay, so if we try to append a value to the list, what is the code gonna do? Well, it's gonna call. So it's gonna call list append on list next, right? So if this is the function call, the original function call, this function is going to call list append on list next, and list next is null, right, which is null, right? But now, what's that function call going to do? Well, since the list pointer that's passed in is now null, it's going to return a new node, right? But back in the original function, right, so it's going to create a new node, but back in the original function call, where we have just called list append recursively, right, we aren't connecting the new node that's returned from this function call to the rest of the list, right? So we're not connecting the new node to the rest of the list, right? And our original list, this node here, still points to null, right? So that's not good. So how can we fix this? Any ideas? Yeah, yep, exactly. So kind of spoiled it a little bit, but this is what we would do. Right, so to make sure that the new node is properly connected to the rest of the list, we do list next equals list append list next value, right? So this ensures that if list append, if we're near the end of our list and list append returns a new node, right, we connect that new node up to our current node, right? So that's how we fix that problem. Okay, so going into a bit of detail on why this works, right? So there are two cases to consider, right, when we are looking at these two lines here, lines 5 and 6, right? So the two cases are the rest of the list is empty, right? So list next is null, and the second case is that the rest of the list is not empty, right? So let's consider the first case where the list is empty. So if the rest of the list is empty, right, then this recursive call, list append, is going to return a new node, right? And then list next equals is going to set the pointer of this node to the new node, right, to point to the new node. So that correctly appends the value to the list. Right? But what happens if the rest of the list is not empty? So that's our second case, right? Then remember, when you're implementing a function recursively, when you make a recursive call, you assume that the recursive call works, right? So let's assume that list appends, this function call here works, and the new value gets appended to the rest of the list, right? So suppose we've appended 5 here, so the 5 goes at the end of the list, and we're assuming that it works. What will happen now is that this recursive call is going to return back. Remember what the function does, right? List append, it appends a value to the rest of the list and returns a pointer to the start, right, of the updated list. So this function call is going to return a pointer back to the start of the updated list, right? And since our current node is already pointing to that node, then this list next equals is not going to have any effect, right? It's just going to set the pointer to itself, right? And that's perfectly fine, right? So that is how this function works. All right. So yeah, that's list append. And if you are a little confused about this, feel free to ask your tutor, okay? And they'll happily explain it. But this pattern of list next equals function call list next is very common if you're trying to solve a linked list problem where you're modifying the list recursively. Right. Okay, and here is an exercise that you can try out that uses a similar pattern. So given a linked list and a value, delete the first instance of the value from the list. Okay? So have a think about how you might solve that recursively, and I'll post the code up on the course website, and you can try it out for yourself. But since it is 12:55 now, we'll stop here and we'll resume on Thursday, all right? Okay, see you then.
question. Can you explain again why we need to start from the head of the leaves when we want to attend the